Okay, so lesson number 5 deals with the Doppler effect, and this is probably one of um, the most famous applications of sound. It's certainly one of the most important applications that we'll look at. And even though you probably haven't realized it, you've probably definitely experienced the Doppler effect. In the mid-1800s, an Austrian physicist, Christian Doppler, explained the apparent change in pitch, or the sound of an object as it passes by with a large speed. So let's imagine the following situation where we have a police car and it's driving down King Street, and its siren is blazing one uniform frequency. So basically we know that these sound waves, when it's traveling at a certain speed, its sound waves, even though it's not going close to the speed of sound, its sound waves will still bunch up, right? Now they're not bunching up a lot. It's not quite like breaking the sound barrier, because this police car isn't going anywhere close to the speed of sound. However, its wave, the crests here, because of its movement, still tend to bunch. They just bunch a little bit instead of bunching a lot. When it's going closer to the speed of sound, these would bunch up and eventually create the sound barrier. Here, we're not going that fast, so they're not bunching quite as much. So maybe this diagram's a little bit exaggerated, but in essence, this is what happens when this is moving in this direction. And so what we end up seeing is that this buildup of sound waves, and if these sound waves build up, it does something to, of course, the wavelength of these sound waves. We know that v is equal to f lambda, so the speed of sound is going to remain constant. And what we notice is that if this remains constant and the sound wave bunch up, i.e. their lambda becomes smaller, their frequency has to become bigger. Okay, so lambda is getting smaller because the sound waves are bunching up, and in response, because v is a constant, the frequency gets larger. So as this police car is moving towards you in this direction, you would notice an increase in pitch. So here's another example of this object moving towards you, where these lines are all bunched up. Object is moving in this direction, and here is an individual listening. It of course works exactly the opposite way when the object is moving away. When the object's moving away from you, these wavelengths, the ones that might be back here, feel like they're more spread out, or they appear to be more spread out. And of course, if the wavelength gets larger, then the frequency must get smaller. So we'd like to be able to determine how the frequency of sound changes for each person, right? So 13.5, section 13.5 in your textbook does have a derivation of the Doppler effect. It's a great derivation if you'd like to take a look at it. But the final formula, and the one that we'll use here, is that F2, the sound that we hear, is given by F1 times the speed of sound, divided by the speed of sound plus or minus the speed of the object. Okay, so first of all, you should note this sign, the plus or minus sign here in the denominator. We use the minus sign when the source is moving towards the listener, and we use the plus sign when the source is moving away from the listener. This would be something that you'd want to commit to memory, or you'd want to put it on a study sheet so that you have it and so that you know how to use it. In this derivation, of course, F1 would be the natural frequency of the source. So the frequency of the train's horn, or the frequency of the car's horn, whatever that is, its natural frequency. F2 is the perceived frequency, as heard by the listener because of this object's velocity. Vs is, of course, the velocity of sound, the speed of sound, and V0 is the velocity of the moving object. So let's take a look at an example. The Batmobile is approaching the Joker at a speed of 140 kilometers per hour, and it's sounding its horn, which has a frequency of 500 hertz. Calculate the apparent frequency heard by the Joker if the speed of sound is 344 meters per second. Well, here's Batman in the Batmobile, sounding his horn, running towards the Joker. We know F1, we know the natural frequency of the Batmobile's horn, we know how fast it's moving. Be careful that this 140 kilometers per hour, we of course convert this into meters per second, because the speed of sound is given in meters per second. it's moving towards the listener. The object is moving towards the listener, and so we're going to use a negative sign in the denominator, and this is something that you should really, when you're setting up what you're given in the problem, this is another piece of information that you're given in the problem, and so it's something that we're going to do. So here's our formula. Now we've removed the plus or minus sign and we've simply replaced it. This is an important piece of communication because this indicates that we understand what's happening in the problem, so we'd always want to include this, and then we put it right here in the formula. We can sub our numbers in, and of course what we should get is we should get a frequency that is, of course, higher, because we know that as we're moving towards an object, that frequency is going to increase, and in fact we do. Our apparent frequency that the Joker hears is 564 hertz, which is higher than the natural frequency of Batmobile's horn. Example number 2 now, the reverse situation. Let's say Robin has fallen out of the Batmobile, and now the Batmobile is driving away. So the same information as before, it's going the same speed, it's just Robin's fallen out. And it's still blasting its horn, but now what frequency is Robin going to hear? And of course we would guess that because the object is moving away from the listener, is that we would hear a frequency that is in fact lower than the natural frequency of the source. And so we can do that. Here's our givens, and this is again exactly the same as from the last problem with one slight change. The source is moving away from the listener, so we would indicate here that this is going to be a positive used in the denominator, and we write our equation with a positive down here, and we sub in our numbers, and we arrive at 449 hertz, which is in fact exactly less and as we expected. Robin hears a lower frequency because the Batmobile is moving